Welcome to my basement. Here's my hot water heater. My hot water heater has some pipes coming out, and one of the pipes coming out is the water that feeds into all of the hot water taps in the house. The hot water heater has a tap here at the bottom, and I just bled out a bunch of water into this bucket here, and we can see that the water in the hot water heater is, I don't know, maybe 50, just shy of 54 degrees C. Let's see how that 53.6 degrees C compares to the water coming out of my hot water tap. All right, welcome to my kitchen. So here I have the hot tap. I'm turning on just the hot water, and I have my thermometer here. I'm measuring the temperature of the water coming out, and seems like we're only about 49 degrees. So where did all that heat go? Well, today we're going to be talking about heat transfer between water and pipes, and how water can, or how fluids can heat up or cool down as they move through pipes. So let's talk about heat transfer between fluids and pipes. So what are we going to talk about first? Well, first we're going to talk about why we care. Perhaps some applications, especially ones relevant to engineering, and in particular bioengineering. Then we're going to talk about, we're going to do an example problem. Then we're going to talk about two common heating conditions that we're able to model heat transfer between fluids and pipes. And those two common conditions, one is what happens when, how does heat transfer occur when your surface temperature, the surface temperature of your pipe, is constant? How does temperature vary along the length of the pipe in that case? And then another case we're going to talk about is what happens when you have a constant heat flux. So we might call that like a Q double prime, like a constant heat flux. I guess you could just call it a Q if you wanted to as well. Use the notation we've done. So basically you get two different situations here. This is the one we're going to talk about mostly in the context of this class. So we're going to do a derivation or example problem, I guess, depending on how you interpret it. But we're basically going to derive the temperature profile along the pipe, the temperature of the fluid, as a function of x, or essentially as a function of the position down the pipe. How does temperature vary along the length of the pipe if we have this constant surface temperature situation? And the strategy we're going to use to solve this problem, well, first we're going to define a shell. Right? If you're looking to derive a temperature profile, temperature as a function of position, shells is generally a pretty good strategy to do so. So we're going to define a shell. Once we define the shell, we're going to do conservation of energy on that shell. And the conservation of energy is going to be made up. We're really just going to be looking at the steady state. Where we've left the tap on for a while and temperatures have stabilized. We're looking at that sort of situation here. So when we do conservation of energy, primarily we're going to be concerned with our ins and our outs. And the ins and outs in this case, we're going to have surface convection. We're going to have surface convection basically between the solid wall and the fluid flowing through the pipe. And we're also going to have energy carried by mass. So if we consider a shell like this, we're going to have energy carried by mass going in, energy carried by mass going out, and they might be different from one another. So our ins and our outs are going to be composed of surface convection and energy carried by mass. So we're basically going to have those as contributions, both of them as contributions for ins and outs in our shell. Once we get this shell conservation of energy and ins and outs all worked out, then we'll end up with a differential equation. So we'll end up with a differential equation, and this differential equation will essentially be for temperature and x. So we'll have this differential equation where we have derivatives of temperature with respect to x, and when we solve that differential equation, that's going to give us this temperature as a function of position. So we'll get this differential equation. We'll have this. We'll get a solution. We'll talk about boundary conditions. But the solution, there's going to be a little bit of a caveat here. We'll have an almost complete solution today. And, I'll unfortunately leave you a little bit of on a cliffhanger. It turns out that there's going to be some trickiness. Some trickiness with H, or the convection coefficient, right? So we basically said, there's going to be convection between the fluid and the pipe. It turns out there's going to be a little bit of trickiness with H that's going to prevent us from getting all the way to a solution. But this trickiness with H is basically going to set the stage for our next few lectures. So, for now we're basically going to say, okay, let's pretend we know H, but the next couple of lectures are going to be, okay, how could I sort of get my own H? So that's the plan. Heat transfer between fluids and pipes. Let's start off by talking about why we care. So under what conditions, or under what engineering applications or bioengineering applications might we encounter, heat transfer between fluids and pipes? Well, the first of which is basically occurring in my body, in our bodies right now. So if I walked outside on a chilly day, that air would sort of be cooling my hands, and you can feel your hands get cold after a while, but your hands would actually get a lot colder than they would otherwise if it weren't for the blood pumping through your fingers. So you basically have the skin of your fingers being pretty cold, but if you have blood pumping through all of your capillaries and your other blood vessels, that blood starts off at your core, which is pretty warm, and that hot blood transfers some of its heat to the surrounding tissues on its way through your finger, and then returns to your core a little bit colder to warm up. So blood's useful not just for circulating oxygen and other chemicals around our body, but circulating heat as well. So an important application is the heating that blood provides and capillaries. Right, so that might be an interesting heat transfer problem from a biological perspective. Bioengineers also might care about controlling chemical reactions. Right, and maybe these are chemical reactions in inside cells, right? So, a lot of times you might maybe, for example, have an incubator. You want to keep that incubator at 37 degrees C to keep your cells happy. Or, if you're sort of maybe in drug synthesis or polymer synthesis or things like that, a lot of these chemical reactions, all of those rate constants depend on temperature. So whether you're actually flowing the reactants through the pipes, or having pipes that essentially surround some reaction vessel or some incubator, and you're flowing fluid through those, the heat that can be passed through the pipes to help either heat or cool chemical reactions is super important for bioengineers, whether those chemical reactions are ones occurring in reactors or in cells. So we care a lot about controlling chemical reactions, and one way to basically control temperature is by running coolant or heating fluid through pipes. In my computer right now, there are pipes with liquid flowing, so we care a lot about cooling electronics. And these electronics might be, for example, electronic medical devices. So those can be very important. So a lot of times those are cooled by liquid coolant flowing through pipes. And this is, I guess, less of a bioengineering example, but in the video that sort of prefaced this segment, I had pipes in the basement of my house carrying hot water to various locations. So we might care about hot water for homes, or heating systems for homes in general. So under all of these circumstances, we might have some liquid or some gas flowing through a tube, and the temperature of the tube and the gas being different from one another and transferring heat between one another. And as bioengineers, we ought to be able to describe that, predict relationships between heat flows and temperature differences and all that. So that's what we care about. So when we're talking about heat being transferred between pipes and tubes, there are basically two common conditions that we might encounter. So I'll just sort of qualitatively describe what they are. So the first one is a constant surface temperature of the pipe, and the second one is constant heat flux. From the pipe surface. So what might this constant surface temperature of a pipe look like? Well, let's say I have some pipe and I have some fluid going in. This fluid might have some temperature of the fluid going in, and that temperature might hypothetically be different from the surface temperature of the pipe. So I might be interested in, hey, what is the temperature of the fluid as a function of position down the tube? Right, and let's say the fluid comes in cold. Just as an example, let's say the fluid comes in cold, and the surface temperature is hotter. Right, so maybe I have my fluid start out at T in, but we know that eventually, very far down the position, if this pipe is long enough, eventually all the fluid within that pipe is going to approach my surface temperature. So, maybe Ts is like this. I'm going to start at Tn and approach Ts. But, we might ask ourselves, well, okay, after what length do we get sort of, close enough to our surface temperature that we care about it? At how long does this pipe need to be in order for the fluid coming out to be, for all intents and purposes, 99% of the way towards our surface temperature? So we might care about predicting temperature as a function of position of the fluid in this pipe. And this is what we're going to spend most of our lecture doing today. I just wanted to contrast that to a different case where maybe I have some pipe, I have some fluid going in, and I've wrapped this pipe in, let's say, like an electric heating coil. Right? So let's say there's an electric heater, and this electric heater might be providing, like every inch of this heater essentially, or every square centimeter of this heater essentially applies a certain number of watts that eventually that flow into this, right? So basically the heater provides watts per square meter, some constant watts per square meter that basically flow into the fluid. And I might care about, what is the relationship between the heat, that this heater is flowing into the fluid, and maybe, for example, what temperature that fluid has as it's moving along, right? So if I were to predict what my temperature of my fluid is as a function of position down the tube, this fluid might start off at T in, but its temperature is going to sort of be raised indefinitely, and and the longer the tube is, the more heat is going in and going in and going in. So unlike this situation of the constant surface temperature pipe, where basically the fluid eventually approaches this surface temperature, here, heat goes in, more heat goes in, more heat goes in. This temperature keeps going up and up and up and up. So these are basically the two situations. And when we go down the road a little bit, both types of systems might be important in bioengineering applications. This is a system where like mechanically it's pretty straightforward to construct a system that looks like this. I just wrap the tube in some heater, I turn on that heater to be some certain number of watts, and and this is a relationship that would exist for temperature. Alternatively, I could have some tube that's sort of going through a bath that's at some constant temperature, and maybe that bath at constant temperature basically prescribes the surface temperature here, or I have combinations of heaters and temperature sensors that basically maintain this particular TS. So you can imagine, both situations might be useful in bioengineering. This one's nice because I know the temperature of the fluid isn't ever going to get hotter than this surface temperature of the pipe. This one might be a little bit more advantageous in some situations because it's a little more straightforward to implement. But, in the context of this class, we might care about modeling both of them. But for the purposes of explanation and in the interest of time, I'm really only going to focus my discussion on this one today. So let's formulate this problem a little more rigorously. And in doing so, we'll set the stage for deriving temperature as a function of position along that pipe. So let's say I have some tube, some pipe, and I know or could measure some particular parameters about this system. So let's say I know the fluid temperature that's going into the tube. I know basically what temperature that fluid starts off going into the tube. This is basically equivalent to whatever temperature I had in my hot water heater. When I measure that temperature, that temperature of the fluid going into the tube. Let's say this tube has some different surface temperature, and we're looking at the case where this surface temperature is some known constant. Let's say I know the cross-sectional area of my pipe, and let's say I also know the perimeter. That I'm gonna call P right here. So I know the perimeter of my pipe, P. I guess if this were a circular pipe, it would be pretty straightforward to just say pi times the diameter. Cross-sectional area would be pretty straightforward in terms of pi over 4d squared for the diameter. But let's just sort of leave these as arbitrary for now, because this type of analysis could be applied for square tubes or something like that. Let's say I know the average velocity of the fluid going into that pipe. And let's say I also knew some properties of the fluid that might be important. For example, the fluid's density, the fluid's specific heat, Cp, the fluid's thermal conductivity, and as well as the fluid's viscosity. So these are all the properties that I would need to know. And then let's say I know the overall length of my tube L. I would want to know, hey, what is the average temperature of the fluid? What is the average temperature of the fluid coming out of that pipe, right? We know if the pipe is going to be super duper long, that fluid is all eventually going to be TS. But if this pipe isn't infinitely long, what temperature does that fluid come out at? How hot is the fluid coming out of the hot water tap in my kitchen? Something like that. So these are basically the problem. These are the parameters that we have, and our goal is essentially to figure out what it is at the outlet. A step on the way towards figuring out that goal is essentially just a picture to derive an expression for temperature as a function of position x, and then we can basically evaluate that at x equals L to essentially get this outlet temperature right here. So this is the plan. What's up next Well, I need to be a little bit more careful about talking about this T of x, because strictly speaking, we know, hey, if this fluid comes in at T in, maybe the fluid in the middle is at a slightly different temperature than the fluid coming at the the fluid right next to the pipe, right? If I think about the molecules of fluid immediately next to the surface, those fluid molecules are probably pretty close to Ts, whereas maybe fluid in the center is a little bit different. So I'm going to need a slightly better or a slightly more rigorous of what temperature I'm talking about, because fluid temperature probably varies. Across the cross section. Right, so across the cross section of the pipe, fluid temperature probably varies, right? The core temperature, the fluid at the core is probably closer to Tn. The fluid closer to the edge is probably closer to Ts. So if I'm, talking about, average temperatures of the fluid, here, things are going to get a little bit messy. So how do I define an average temperature? So first, what I'm going to do is I'm actually going to explain, I'm going to give the wrong definition first to contrast this with the correct definition. So one way I might think about, so the wrong way to think about an average temperature is, hey, if I just looked at the cross section, of this pipe and said, hey, each little point on the cross section, each little point on this cross section has a different temperature, right? There's, one temperature here, 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 right? If I just took all of the points along the cross section and averaged them and, sort of added them up and then divided it by the cross-sectional area, I could get a definition that might look like this. I could essentially integrate the temperatures over the cross-sectional area, essentially multiplying each little temperature times the little dA that it belongs to, and I could divide that thing by the whole cross-section. That could give me a definition. It turns out that this is actually the wrong definition to use here. Why is it the wrong definition? Well, it turns out that the fluid in the center is moving faster than the fluid at the edge, right? If I think about it, if I dust off my notes from the fluid mechanics part of this course, we had this parabolic velocity profile if flow is laminar, and then something similar but not exactly the same if the flow is turbulent. So, shouldn't this flow that's going through the center, shouldn't I weight these temperatures in the center a little bit higher than the temperatures at the edges for considering this average, because more flow is actually going through the center, right? So the correct definition basically accounts for more flow in the center, and it's what we call the mean mixed definition for T sub m, and this T sub m stands for mean mixed, and you can basically think of this as an average. And basically what this mean mixed temperature is if I cut the pipe off, it's, if I had my pipe right here, fluids flowing through that pipe, if I just cut that pipe, threw away whatever was coming out, and then took that pipe and poured its contents into a bucket and swirled around that bucket until I totally mixed whatever was coming out in that bucket, that temperature of what's in the bucket would basically be this mean mixed temperature that I'm talking about. And of course, this mean mixed temperature accounts for I'm sort of accounting for the fact that all of the temperatures might vary across the cross-section of the pipe, but also the fact that the flow is faster in the center compared to the edges. So, if the flow is faster in the center, more of that flow is gonna enter this bucket. So those temperatures are weighted a little more heavily. So what is this mean mixed definition? I'll put it down in the notes, even though we won't end up really using it too much. This mean mixed temperature is defined as an integral over the cross-sectional area of temperature times x velocity, dA, divided by an integral over the cross-sectional area of just Vx times dA. And if you notice, this bottom is essentially just the definition of the volumetric flow rate. So it's the volumetric, so it's this top kind of goofy thing, this sort of velocity-weighted average of temperature divided by flow rate. So anyway, here's the definition. What you can think about it is just basically on average, what is the temperature of the fluid flowing through some particular slice? This is really the way to think about it. It's just what is the average temperature of the fluid flowing through one particular slice in the pipe. So what do I mean? So if I'm looking, if I want to think about temperature of the fluid, strictly speaking, temperature of the fluid in my pipe is a function of x and my radial position r, right? The fluid in the middle might be different from the fluid close to the edge, but if I think about my mean mixed temperature, this mean mixed, I'm essentially averaging over, over R. So the mean mixed temperature is basically going to be just a function of x only. So this would be a pretty complicated derivation to have to do, really beyond the scope of what topics we're covering in this class. But mean mixed temperature, hey, let's just try to figure out what this mean mixed temperature is as a function of just one variable, x. This is doable. And in fact, we're going to do it now. So if I want to think about it, hey, if I want to derive what this mean mixed temperature is as a function of x, I want to derive temperature as a function of some spatial variable. Anytime I want to derive temperature as a function of x, or velocity as a function of x, or something as a function of some spatial variable, this basically should be standing out to you. What problem-solving strategy should I use? Shells, right? Shells will do this. And if I want to do temperature, the best way to figure out temperature is shells with conservation of energy. So what are we going to do now? Let's define a shell. So if I want to derive temperature as a function of x, I want to define a shell where I choose x as my delta dimension. Right, so temperature is going to vary with x. I want to choose x as my delta dimension. So I'm basically going to define what this shell is going to look like. I'm basically going to imagine my pipe, or the fluid within my pipe, as essentially a stack of quarters or something like that, where one of those quarters is basically going to be this shell right here, and this shell basically has a thickness delta x, and it sort of encompasses the full cross-sectional area here. So I'll draw it a little bit bigger. This is my shell right here. I basically have an upstream face at location x, a downstream face at location x plus delta x, because the thickness of this shell is delta x. I basically have fluid flowing into one face and fluid flowing out of the other face, and convection, surface convection, happening between the pipe and the edge of this chunk of fluid right there. So let's think about how we might formulate conservation of energy for this shell. So conservation of energy, I mean, we could write out the full messy form that I had in that first version of the notes, but I like the shorthand. Accumulation equals ins minus outs plus generation. So can we cross out any of these terms to begin with? Why, yes, we can. Right? We said at the beginning of this lesson, we were just really looking at the steady case right here. So if I think about steady, I can cross off my accumulation term. Right, so steady is gonna get rid of this term, and then if I'm looking at it, if we had chemical reactions going on in this tube, then things would be a bit of a hot mess. So right now, let's just sort of consider the case where we don't have chemical reactions, and because our shell is sort of entirely within the fluid, any sort of heaters are external to our shell. So we basically have like no reactions, no heaters within this shell right here. So at that point, we're just looking to balance ins and outs. So let's take a closer look at our ins and outs. As we talked about in the beginning of the section, we're basically going to have surface convection between the solid pipe surface and the fluid flowing inside the pipe. And also, we're going to have energy carried by mass in this system as well. All right, so what's going on? Well, essentially, I have fluid flowing into this upstream face and fluid flowing out of this downstream face. So I'm going to have essentially energy carried by mass entering into this face and energy carried by mass leaving this face right here. And I'm just going to call the energy carried by mass, I'm just going to call it E dot, for lack of a better variable. And it's essentially an energy carried by mass. So for this upstream face, it would be energy carried by mass at position x. And for this downstream face, it would be energy carried by mass evaluated at x plus delta x. So, and these two might not necessarily be the same as each other, in particular because I'm going to have heat due to convection. So take a moment now, pause and ponder. Draw the arrow for convection. Draw the arrow for convection for this system right here. Right? In the same way that I drew arrows for these mass. Draw the arrow for convection. Well, what might this arrow for convection look like? It's going to be entering through the side. Wait a second, entering, you say? This is different from the fin that we talked about earlier. Well, it's entering because by definition, convection is from the solid surface to the fluid. So convection is going from the pipe to the fluid by definition. It goes, convection is from the solid to the fluid by definition. So this is basically going to be my Q dot convection entering through this side area right here. So I have energy carried by mass in, energy carried by mass out. In is at x, out is at x plus delta x, and I have convection, surface convection, coming in from the side, and that's an in because it's coming from the solid pipe into the fluid, which is our control volume right here. So my accumulation equals ins minus outs plus generation. I have 2 ins and I have 1 out. So my conservation of energy equation ends up becoming 0 equals energy carried by mass evaluated at x minus energy carried by mass evaluated at x plus delta x. And these are rates, these are energy rates. All these terms are going to have watts, plus our Q dot convection, which is an in, and that's coming in the sides. So this is conservation of energy that we have right here. So let's now take our next steps in terms of developing, trying to put some of these terms maybe in terms of some of these constants, some of these known constants or parameters that we care about in the problem. All right, so let's go ahead and do that. So let's do the easier one. Well, I mean, they're not super easy, but let's do the easier one first. Let's talk about convection. So take a moment now, think about convection here, think about some of the geometry of our control volume and some of the given parameters. See if you can work out, pause and ponder, see if you can work out what q dot convection might look like. Well, here, let's talk about it. For convection, we can use Newton's law of cooling. So q dot convection is equal to h times the surface area times Ts minus T infinity. Well, let's take a closer look at some of these terms here. Well, Ts is just a known constant right here, so we can work that out, right? We can just sort of say, hey, Ts is our known constant right here. What about T infinity? Is there a well-defined T infinity for fluid right here? Well, there isn't, right? There's not some fluid kind of far away from our surface that we're really talking about. The only fluid that we're talking about is the fluid within the pipe. So it turns out for flow through a pipe, we use a slightly modified version of Newton's law of cooling, where instead of a T infinity, it's basically a Ts minus our mean. Our mean mixed temperature, this mean mixed Tm that we're talking about here, right? So instead of T infinity, it's basically Tm, and this is going to help us out because here we essentially have a way to sort of get Tm into our conservation of energy equation. So hopefully this is going to build towards, an equation that involves Tm that we can basically use to predict Tm. I'm just going to leave h as some as of yet unknown constant. Spoiler alert, in a couple of lectures, we're going to be actually able to find our own h in terms of things like velocity and perimeter and cross-sectional area and density, specific heat, K-fluid, and all this. So for right now, I'm just going to leave it as h. In a couple of lectures, we're actually going to be able to find our own h, which is going to be super awesome. Then finally, if I think about the surface area, it's the surface area through which convection is going. So what is it going to be? It's basically going to be if I took this surface here and unwrapped it and formed it in a rectangle. So that surface area is basically going to be delta x times the perimeter of whatever this pipe is. And if it were a circular pipe, it would be pi d. But I'm just going to put perimeter as its own known constant for now. So q dot convection for our shell is going to be this. Let's now take a look at our energy carried by mass. Well, we can plug in our convection into this equation, and what do we get? We basically get 0 equals energy carried by mass at x minus energy carried by mass at x plus delta x plus h times delta x times p times Ts minus Tm. All right, so what can I do? I can basically divide by x, and I can rearrange some of these terms here. So what do I end up with? I basically end up with minus E mass at x plus delta x minus E dot mass at x divided by delta x plus h times p times Ts minus Tm. So some of you should be like, hey, wait a second, this is like the oldest trick in the book right here, right? We've seen this a million times. this is basically looking like the definition of a derivative. So I can replace this with a derivative by taking limits as delta x goes to 0. So when I take limits as delta x goes to 0, I get d e dot mass dx plus h times p times ts minus tm. All right, great. I have a differential equation, but I was hoping to have a differential equation for temperature in x. What I have instead is a differential equation for energy carried by mass, and temperature appears somewhere in it. So my hope is to basically say, hey, can I get an expression for what this energy carried by mass is, right? Can I try to put this in terms of T, and hopefully in terms of Tm? Well, yes, I can. So what might that look like? Well, the energy carried by mass is going to be proportional to a couple things, right? If I think about, how much energy is carried by the fluid going into this surface, it's going to be proportional to a couple of things. Well, the first thing this energy carried by mass is going to be proportional to is the temperature of the fluid, of that fluid going in, right? The hotter the fluid is, on average, going in, the more energy I have, the more thermal energy I have going in. So energy carried by mass is going to first be proportional to temperature. But if I start thinking about units, right, this energy carried by mass is going to have units of joules per second, or watts, as is true, this energy carried by mass is going to have units of watts, or joules per second, and the mean mixed temperature is basically just going to have units of Kelvin. So I'm going to need a couple of other factors on this other side here. Right, well, what else is this energy carried by mass proportional to? Well, it's proportional to the velocity. The faster fluid is entering, the faster the rate at which the thermal energy carried by that fluid is entering. So a second thing that this thing is proportional to is the average velocity of the fluid. What else is this proportional to? It's also proportional to the cross-sectional area. The more area I have, the bigger pipe I have, the more energy is entering that at some particular time. So my cross-sectional area is there. So my velocity, that's going to be meters per second. My cross-sectional area is meters squared. I'm still not all the way there. What else might this be proportional to? Well, we said if we're thinking about fluid carrying energy with it, the specific heat is going to be important for this process as well, right? So what is specific heat? It's basically the thermal energy carried by fluid, or the energy required to raise the temperature of fluid by some amount of temperature, a certain mass of fluid by some certain temperature, and this basically has units of joules per kilogram Kelvin. So if I think about it, kelvins are going to cancel, but I still have kilograms in the denominator here, and then meters squared, and seconds. So what else am I going to need? I'm also going to need the density of the fluid, right? If the fluid has a greater mass density, then there's more mass entering and more mass exiting. So more mass entering basically means more thermal energy entering. So density is going to have units of kilograms per meter cubed, and if I look at all the units, kilograms and kilograms cancel, Kelvin and Kelvin cancel, meters squared in the numerator and meters cubed in the denominator cancel, and I end up with joules per second. So this is my energy carried by mass. So I could plug that into this equation up here, so then I have minus d dx of Tm, velocity, cross-sectional area, specific heat, and density, and then I have plus this second term here, which is sort of unaffected, h times p times ts minus tm. That's here. All right, so now I have a differential equation. I'm making progress here, and I think about it, this derivative is going to get a little bit simpler if all of these things are constant with respect to x. I can basically pull out if they don't vary with x. And in particular, they need to not vary with x, but also not vary with temperature too, right? If temperature varies with x, then these things will sort of implicitly vary with x. But if I make the assumption that these constants are indeed constant, then I can pull them on out. And if I pull them on out, I get the following differential equation. That might be a little bit easier to solve. So if I pull it out and do a little bit of rearranging, I end up with dTm dx is equal to perimeter divided by density times specific heat times average velocity times cross-sectional area, and then this thing times h times Ts minus Tm. So this is my differential equation right here. Sweet. So, one quick thing. If I go back to this step, you might be like, hey, wait a second, why'd you use ordinary derivatives? I thought we were supposed to do partial derivatives when we pulled this delta business. Well, this mass flow rate is sort of dependent on temperature, and we were saying this mean mixed temperature is only a function of x. So that's why I used ordinary derivatives. So strictly speaking, it would be partial derivatives, but we already concluded that mean mixed temperature is only going to be a function of x. So that means we can have ordinary derivatives right here. So I have this differential equation. How do I go about solving this differential equation? I can do separation of variables, where I can bring the t stuff on one side and the x stuff on the other. So I get dTm divided by Tm minus Ts. Note here I flipped the order of these two terms, so I basically can pull out a negative sign. So on the right-hand side, I end up with minus p over rho Cp average velocity AC times h and a dx right here. So I separated my variables. I can integrate. So I can, integrate here on both sides. So I essentially have two strategies that I could do here. I could leave these as indefinite integrals, and then when I do these indefinite integrals, I would get a plus constant. Or I can put these in terms of definite integrals and just sort of have corresponding limits of integration. So, we've done the former strategy a couple times. Let's try out the other strategy here. So, what might I think about it? At x equals 0, what temperature corresponds to x equals 0? Well, the temperature that corresponds to x equals 0 is our inlet temperature. And this essentially is a boundary condition, right? So what are we doing now? We got our differential equation. We're solving it. Instead of sort of getting constants and solving for those constants with boundary conditions, I'm just kind of including the boundary conditions within the limits of integration. So the boundary condition is essentially at x equals 0, my temperature is going to be Tin. And then I can say, hey, this goes from 0 to x equals L. If I cared about my outlet temperature, I would evaluate it at x equals L, and I can say, hey, there's some average temperature. At x equals L, I get my temperature is going to be my average outlet temperature, which is what I wanted to solve for. Cool. So we have these integrals. We can do these limits of integration. Let's see what we get with integrating. Well, strictly speaking, on this left-hand side, I would need to do a u substitution, right? I'm essentially, if I just covered up Ts, I'm essentially integrating 1 over Tm. So when I integrate 1 over Tm, I'd get natural log of Tm. Strictly speaking, I'd need to do a u substitution, but I'll just kind of cut to the result right here. So what do I get? I basically get Tm minus Ts, and this thing evaluated at Tm equals T in to Tm equals T average out. And then on the right hand side, well, I can pull out a lot of this junk from the integral, right? So a lot of this stuff, all of these things, I think I said it was assuming constant with respect to x, so I can pull those things out of the integral. And you know, what do I do if I can do that? I basically get like minus p over rho cp average velocity times cross-sectional area. And then what am I left with right here? I'm left with an integral from 0 to L of h. So take a moment now, pause and ponder. Will h vary with x? You know, under what circumstances might h vary with x? Under what circumstances might h not vary with x? If h doesn't vary with x, you know, could we, you know, we could pull it out of the integral, but, you know, might h vary with x? Well, hopefully you've had a chance to think about it. H can and actually does vary with x under a lot of circumstances. So imagine my pipe right here. A lot of times initially when fluid enters a pipe, it might enter uniformly, but downstream that fluid might, you know, if the flow is laminar, become this parabolic velocity profile. So fluid entering basically enters uniformly, and then eventually it kind of becomes laminar, and there's this sort of transition region where you can almost imagine boundary layers sort of growing from the edge, where basically fluid that enters fast, you know, fluid sort of enters fast at the edge and then eventually gets pushed towards the center. So at some inlet, some entrance length, of the pipe, we get a very different fluid flow. And then after your entrance length, your flow, you know, if it's laminar, is parabolic, and then continues to be parabolic after every point after. So there's this sort of entrance length effect. And it turns out that because you have fluid entering close to the edge and getting pushed towards the center, that fluid getting pushed towards the center basically enhances our heat transfer. It enhances our convection coefficient just within the entrance length. So for, you know, does h vary with x? Yes. In the entrance length, h is actually a little bit bigger than the h ends up being farther along. And this, you know, this can be a little bit messy. But, you know, but are we going to let this halt our progress on this entire problem? No, let's not let it halt the entire problem. Let's sort of move on a little bit. Oh, sorry, I had here, this isn't Tm minus Ts. Sorry, this should be natural log. Oh my goodness. This should be natural log, right? Integrating 1 over Tm gives natural log of this thing. Sorry. And then going back to this right-hand side, you know, I can basically say, hey, strictly speaking, I know h varies with x, but instead what I'm going to do is I'm going to call this integral of h from 0 to L, I'm just going to call this L times, sorry, oops, oh my god, I'm making so many mistakes. I'm going to call this quantity right here, I'm going to call it L times what I'll call h bar, where h bar is averaged over the length of tube. Right, so strictly speaking, we have a slightly higher h at the beginning, but if I take that h and sort of average it over the whole L, then the averaged h over that whole L is what I'm going to call h bar. And L times h bar is essentially the integral of h from 0 to L over x. So what is that going to look like? If I evaluate the left-hand side, I basically get natural log of T average at my outlet minus Ts minus the natural log, so minus, right, minus the lower limit of integration, which is going to be natural log of T in. When I sub T in for Tm, I get T in minus Ts. And then this is going to be equal to the right-hand side, which is basically minus P over rho Cp V AC times L times h bar. I can take this equation and I can solve it, maybe solve it for T average out. So what do I get if I do that? Well, anytime you have subtractions of natural logs, that's equivalent to dividing to a single natural log of, you know, this in the numerator and that in the denominator. So if, you know, you dust off your pre-calculus notes back from high school, if you subtract two natural logs, then that's equivalent to dividing the contents of the two. And then I have basically natural log of these things divided by each other. I can exponentiate both sides. So what does that give me? That basically gives me T average of my outlet minus Ts divided by T in minus Ts. That's equal to, if I then exponentiate both sides, I get e to the minus p over rho times Cp times average velocity or cross-sectional area times L times h bar. So what might this look like? Basically, the longer my tube is, the temperature, you know, the temperature as a function of position is essentially exponential decay. So basically, my temperature starts at T in, and it exponentially approaches my average temperature at the outlet. And that's kind of what I sketched out early here, right? Basically, my T in kind of exponentially approaches Ts. And we could see that, you know, a little more algebraically. If I solve this, I could basically, you know, I could reformulate this right here. You know, instead of basically saying T average at the outlet, I could just replace this with some arbitrary T of x, and I could replace L with some arbitrary x. So what might that look like? My mean mixed temperature as a function of x is equal to the following. It would be T in minus Ts times e to the minus p over rho times Cp times average velocity times cross-sectional area times h bar times x, this whole thing then plus Ts. So that's basically what I get if I, instead of having T average at the outlet, just put this sort of as an arbitrary function of position x, and I put my x right here. So this is this result, and this equation essentially describes this exponential approach from T in to Ts, and as a function of these parameters of the geometry, you know, like perimeter and cross-sectional area, as well as properties of the flow, like its velocity, and the properties of the fluid itself, like density and specific heat, this gives me all the information I need to predict what is the temperature of the fluid flowing through that pipe, the average temperature of the fluid flowing through that pipe as a function of position. And this might, you know, in an engineering context, you know, for problems like this, say, you know, hey, how long does that pipe need to be in order for it to get appreciably close to Ts? Something like that. So, hopefully you found this discussion helpful. Unfortunately, I'm going to leave you a little bit on a cliffhanger, right? So we basically said, hey, you know, we have our solution, our boundary conditions. Here we have this H, which is, you know, which I didn't necessarily give us in the problem statement. You know, here I basically said, hey, you know, we know things like the velocity of the fluid and some properties of the fluid, and some geometry of the pipe. But here I basically said, hey, we're treating h, or h bar, as some known constant. So next time we're basically going to work towards finding h bar as a function of knowns. Knowns in this problem. For example, the average fluid velocity, the fluid density, specific heat, etc. It turns out that this process isn't trivial, but it's doable. So rather than sort of being in these situations where the clouds open up and Professor Lannin's face comes through and says, H is such and such watts per meter squared Kelvin, and then the clouds close back up, we're actually going to be able to find our own H as a function of parameters that are very easy to measure or very easy to look up. You know, I can look up these properties of the fluid. I could take out a pair of calipers and measure, you know, the diameter of a pipe and things like that, right? So these are things that are a lot easier to design. We don't need to rely on being given an H in order to predict this temperatures. But this is going to be the topic of a future lecture. So hopefully you found this lecture helpful in your study of heat transfer. So thank you very much for watching, and good luck with your studies. Cheers.